All right, so this lecture is on current and current density, right? We're just basically defining these terms today, current and current density. We're beginning to look at circuits. This is the very first objective in our circuits unit. That's the third unit, or unit C. And let me briefly show you again that objective on the screen. Right, the one for today is this C.1.A. Students should understand the definition of electric current so they can relate the magnitude and direction of the current to the rate of flow of positive and negative charge. So what is electric current? All right, so just first a definition. Right? Current is just the rate at which charge flows through an area, right? And usually the area we're talking about is the cross section of a wire. Right, so if you kind of pick a point along the wire, what's the rate that charge flows past that point? That's electric current, moving charge. The definition of current, and we use capital I for current. And again, I'm not quite sure why it's a capital I for current. I'm sure I heard the explanation sometime, but I don't remember. But the definition is just it's the rate at which charge flows through the area. So rate is usually going to be a derivative, right? So it's the dq dt, right? The time derivative of the amount of charge at a point. So if the amount of charge that's flowing is constant, or if we kind of want to take an average over a period of time, we can find the average current is just going to be delta Q over delta. All right, so this, our derivative kind of simplifies, as they always do, to delta Q over delta T when we're talking about a period of time that's not infinitesimally small. Right, but this is the definition of current, and that's what I'll put a box around that. So to remind you, need to know it. What do you think just looking at this, what would the unit be for current?
Coulombs per second.
Coulombs per second.
Yeah.
Yeah, go ahead. Right, a coulomb per second, right? It's a charge divided by a time. So the SI unit for current is the coulomb per second, and we have a name. We define a new unit. Anybody know what that is?
Is it amps?
Yeah, amps or amperes, right? So 1 ampere, or usually just call it amps, is 1 coulomb per second. So if you have a coulomb of charge passing through a point in your wire every second, you've got 1 ampere of charge. And unlike, we usually say 1 coulomb of charge is a ridiculously enormous amount of charge, and you'll never really have a coulomb of charge. But an ampere is a pretty reasonable current, actually, because you can have a lot of electrons flowing past the point in a given second. So, an ampere is not kind of a crazy large unit like coulomb is, practically speaking. All right, so that's the basic definition. Yep, go ahead.
Is that because when you have a single length of wire, it's 1 coulomb going through that whole wire and multiple electrons, and that's why you would think 1 ampere is not that big, because you have multiple electrons moving through the wire with a total of just 1 coulomb?
Yeah.
Yeah.
Well, it's also because so in a wire, you've got the electrons are movable, right? Because in a conductor, the electrons aren't really bound very strongly or at all, really, to the protons, right, to the atoms.
Yeah.
But if you think about it, you still have the protons there, right? So there's the wire itself still neutral overall, right? Mm-hmm. So there is a large amount of charge in electrons, but there's an equally large amount of charge in protons.
Okay.
Cool. So that's neutral, but only the electrons are moving, right? So only electrons contribute to the current.
Mm-hmm. All right, thank you.
So we want to get a good expression here for kind of what's gonna affect what is the current flowing through it, like a regular wire, going to depend on? Right, so let's consider a piece of wire. We'll assume it's a cylinder like most wires are. It's got to be conducting, otherwise the charges aren't going to move. Of cross-sectional area A, right? So, and in most wire, that's a pretty small area, right? But we could have a bigger wire as well. It doesn't really matter. But A is the area of the cross section, and we'll say delta X is the length of the piece of wire. And we want to see if we can get a good expression for the average current passing through that wire. And that expression is going to help us tomorrow when we define resistance and resistivity. So we're going to write N, and this is something that we can measure or look up more likely for us for a given material, for a given metal, right? N is just the number of mobile charges, and by mobile charges I mean electrons. In this case, in most cases, per unit volume, right, in this segment, right? And they each, since we're talking about electrons, although this could be, we could do the same thing for some other thing that wasn't necessarily electrons, but that's pretty much all we're going to be dealing with. So each of charge E, right? E is the constant, what is it, 1.6 times 10 to the minus 19 coulombs or something like that is the charge of an electron, right? So that's just a constant. All right, so let's try to get the average current. And remember, we say average current is the charge divided by the time. So let's start by finding the charge. All right, the total charge in that segment. Well, let's see. It's going to be, so if N is the number of mobile charges per unit volume, and they each have charge E, what you might be able to figure out what's an expression then that's going to give us the total charge. Any guesses, or what do I need to know to find the total charge?
You also need to know area, right, in delta X.
Yeah, well, we're saying area and delta X are givens here, right? So we can write it in terms of area and delta X. Bad copy.
I'm trying to find.
Well, this isn't something that we need to look up, or maybe, or we should be able to put this together. So we know we
You
have.
just multiply N by
Okay.
the length of the segment.
So multiply N by the length of the segment. So that's, oh, no problem, Nate. Welcome back. Yeah, if we multiply N times the length of the segment, that's on the right track here. So capital N here is the number of charges per total volume, right? If we want the total charge, we want the number of charges times the charge per charge, right? E. So if N is the number of charges per unit volume, the total number of charges in our wire is N times volume. Let me write this. Right, our charge is going to be N, the number of charges, which is N times the volume. And I wasn't given a volume V, so what would the volume of this piece of wire be? Can we figure that out easily?
Would be the area of the caps times the length.
Yeah, exactly, right? This area times the length will give us the volume. So N times area times delta X, right? That's the number of electrons in the wire right now. And then times the charge for each electron, which is E. All right, so we've got this would give us the total charge in the wire, right, at any time. It's the number of charges per volume, which is usually, pretty going to be constant for a given metal, right? It has to do with the molecular makeup of the metal. Starting to get into chemistry there. But we can figure this out. We're given the area, we're given the length, and we know the charge of an electron. All right. So let me see where. All right, so far.
Yeah.
All right, so next we'll say, okay, we were looking for what's the current, right? So if we know the charge in there, we can find the average current, right, just by dividing by delta T. Let's move on to the next page here. So remember that the average current is the charge divided by the time. So if we just need to divide the time it takes for the charges, right, or the average time it takes for each of those electrons to pass through the segment. Right, so if we do that, we get the average current is going to be Q over delta T, which is N times the area times delta X T divided by the time. So we can simplify this a little bit because we know what's this delta X over delta T. That's a familiar looking.
Velocity?
Yeah, velocity, right? So the delta X over delta T would be the kind of average velocity of the electrons. Okay. And we actually call it the V sub D, so the drift velocity.
Isn't it a very like high number?
Is what?
Isn't it a very like high number?
Yeah, well, actually, we'll do a couple problems where we get some actual numbers for what the drift velocity is, but it's not as high as you might think it would be. Because what we usually have and is in a conductor, even when there's no, if you have a wire, even if the battery is not connected to the wire, the electrons in that wire aren't just sitting still, right? They're constantly moving and bouncing around off of each other and off of the protons that are in the wire, right? And that's actually has to do with the temperature, right? That's thermodynamics, really. Remember, from thermodynamics, temperature is just basically a measure of the average kinetic energy of those particles that are bouncing around. The hotter the wire is, the faster they're going to be moving around. And the drift velocity, if you attach a battery so that the currents are now flowing, that drift velocity is actually really small compared to the speed of the random motion, right? But the random motion, that's in all directions equally, so it basically averages out to zero velocity. But then once you do have a battery attached and you have a current flowing, that's where this drift velocity comes from. Right? So it's kind of important not to think that when there's no current, all these electrons are sitting still, right? Unless you're at absolute zero temperature, they are going to be bouncing around off of each other. They're just not going to be.
And that bouncing creates resistance.
The bounce, well, the resistance, we'll get to. Yeah, let's wait till tomorrow to talk about where the resistance.
Okay.
So that's a good thought. So I just want to, let's see, finish. I just want to substitute this VD back in here for our average current, which is now we can say is equal to N times E, the charge of the electron, times the area of the wire, times the drift velocity of the electrons, right? So this is and I think this is one of the equations on your equation sheet. And this is just the current in a wire, which is the number of electrons per unit volume, which is kind of a property of the material of the wire, times the charge of the electron, times the area of the wire, times the speed, the average velocity of the drift velocity of the electrons. Right? And we're gonna keep going with this equation in just a moment here when we finish, just by talking about current density briefly. But are there any questions or comments so far?
Nah.
All right, so let's finish just by talking about current density, which is just the current per unit area, right? So you can think for the same current, if you have this big giant wire, right, there's not as much current flowing through it through any, given piece of that cross section. So it's got a smaller current density than if you had that same current traveling through a tiny little wire. And current density is gonna come into play when we talk about resistance and resistivity tomorrow. But it's the current per unit area. So let's just come up with, well, the definition for current density. Another kind of odd choice for symbol for current density here is capital J. But it's just the current divided by the area. So if we go to if we plug in our equation here, right? So this is a definition for current density. That's the important one. And then if we plug into here for a cylindrical wire like we've been talking about, we just divide out the area, right? It's just the number of electrons per unit area times the charge of each electron. Right? We divide the area out, so just times the drift velocity to get the current density. And that, I think, is where we're going to stop the lecture for today. We're going to use this equation for current density tomorrow when we kind of come up with our relations for resistance, and we're going to learn Ohm's law. But I think we're going to stop here today with current and current density. So any last questions or comments on this?
I'm still having a bit trouble trying to understand why we're using the derivative for 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 the current.
Why this?
So it's because all the math that we just did was trying to find the amount of electrons going through and then dividing that by the time to find almost the speed.
Yeah, so most of the work we've been doing here to get this equation and the drift velocity, we're kind of assuming that either, this will be valid either if we're talking about a constant current, right? So then if the amount of charge isn't changing over
Right.
time, then this derivative is going to simply become just charge over time. Right? But in the general case, you could have, and when we start doing circuits with capacitors in it, we'll see that the current does change over time. Like the amount of charge flowing to point isn't constant over time. So in that case, to get the instantaneous current, we would need to take the derivative.
Okay. So then, all right. So say it was constant, and we do change in q over change in time. But then the change in q would be 0.
If it's not so you're saying
It is constant.
Oh, so no, I'm not saying that the change in Q is 0, but I think I see what you're saying. It's more maybe the delta here is confusing. It might be clear to write just Q over time instead of delta Q over time. But what we're saying though is the total amount of, right, in this Q over time, this would be the total amount of charge that passes through the wire divided by the amount of time it takes.
Right. Okay.
And that's going to be, even if that's changing over time, right? If we're talking about a finite amount of time, we'll still get the average current, right? Even if it's changing, this will still give us the average current.
Right.
In the case where it's not changing over time, then the average current will always be equal to the instantaneous current.
Right.
Does that answer your question well?
A little bit. Yeah. I mean, I'll just have to figure it out on my own.
And it's kind of the same. It's kind of the same. You can make the analogy to velocity and average velocity, right? Velocity is our instantaneous velocity is dx dt, right? But the average velocity is always going to be delta x over delta t, and that's going to be accurate even if your velocity is changing. It'll still give you the average velocity over the time.
Right. Okay.
All right, so let me stop the lecture here and we'll move on to the problem reviews for today.